Hi, in this video, we're going to analyze this circuit over here. This is a common drain JFET based amplifier. All right. So the input feeds into the gate, and the output comes out from the source. Now we're gonna derive expressions for Zi input impedance seen from VI, the output impedance seen from VO, the voltage gain, and the current gain of the circuit. All right. So I/O is a current that flows from uh, across RS, yeah, and II is the input current that flows from VI into the gate. Okay. So as usual, whenever we're trying to do an AC analysis, we convert our DC circuit into an equivalent AC circuit, and these are the three steps that you must do. So the first is we should short all capacitors. That's in this case it's C1 and C2. We should zero all DC sources. In this case, it's only VDD. And finally, replace transistors with the AC equivalent model. So in this case, this JFET is modeled by this circuit here. So you have a simple single component dependent current source of GM VGS connected between the drain and source. All right, so let's have a look at what this side would look like. If you remember, VDD needs to be grounded, which means the drain part is going to be connected to ground, i.e. 0 volts, right? So VDD is going to be 0 volts. So the drain part is going to be connected to ground. That means down here. C2 will be a short, and RS will be just a resistor that's connected from the source to ground. So let's have a look at that side. So we have the drain connected to ground, and the RS is connected from the source to ground. So IO is still where it is. ZO and VO are still where they are. All right. And on the left side, on the input side, we have an RG that is connected between gate and ground, and C1 is a short, so VI directly connects to the gate. So, like so. All right. Okay, so let's figure out a few components here. So, as usual, we'll figure out what IO, II, VO, VIs are. All right. And then from those parts, we then go and figure out what these four components should be. All right. So let's start with IO. So IO is a current that flows, in this case, going up. There's nowhere else to go but continue through here and into drain, right? So if you notice, there is a downward current called GMVGS that is in opposite direction to IO. So IO is just the opposite of GMVGS. All right, so IO is simply the negative of GMVGS, right? All right. Now, now let's have a look at. Well, usually I look at II, but II would need information from VI and ZI. So maybe we can look at VI first for now. All right. So we can use KVL. So VI is a voltage drop from gate from here to ground. So you can also express it in this form. So there's a VGS plus the voltage across RS, right? So those two added together becomes VI. So we can use KVL to define what VI to be. So we have a VGS plus the voltage across here. So that's going to be IORS, right? So it's going to be, it will be negative IORS rather, because we want the voltage to be pointing up. So IO needs to be pointing down, all right, to get a positive voltage across RS that's pointing up, all right? So, I mean, I can write here as VRS, okay? So then VGS is still VGS. plus now VRS, it's just Ohm's law. V equals I times R rather, where I is GM/VGS and R is RS. Okay, we can factor out VGS, so then it just becomes 1 plus GM RS. Okay, so that's our VI. So now we can have a look at II. Okay, so we can look at II. We'll use Ohm's law for this. So for II, well, I equals V over R, so we just use Ohm's law. So VI divided by ZI. Okay. Okay. We could do it like that. All right. But then we don't know what ZI is yet. So maybe another way would be to just simply look at the current that is flowing. Okay. So we know that this II current will not go to the gate because the gate is basically an open circuit. So there's no current going through the gate. So what II will do will just come through RG. All right. So therefore, we can say that II is VI over RG. Right. Okay. So we have an expression for VI, which is this thing at the top here. So we can write here as that divided by RG. Okay. So that is our expression for II. So next, let's have a look at VO. That's the voltage on the output side, VO. And again, we can write it as negative IO times RS, right? So IO is actually pointing up. So since we want VO positive pointing up, then IO needs to be pointing down, all right? So again, this is just Ohm's law. So VO is equal to V equals IR, so it's negative IO times RS, right? And we have IO, which is negative GM/VGS, so therefore it's just negative becomes positive, so GM/VGS times RS. Okay. Okay, so then now that we have those four equations up, let's go and work out these guys, right? So let's have a look at, first of all, the input impedance. All right, so the input impedance is here. Well, I mean, it should be quite obvious. The only thing that the input voltage is going to see in terms of impedance is just going to be RG, because this is an open circuit, so therefore there's nothing else that you can see. So except for RG. So that's ZI done. Let's have a look at ZO. Okay, so ZO is what? Well, now ZO is if you guys remember, whenever we're working out the output impedance, we have to zero the input signal. Yeah, we have to zero VI. Okay. Okay, so now this we need to be careful here. When you have VI 0, I mean, based on this equation up here, yeah, VI is equal to VGS 1 plus GMRS. You're gonna have, or rather, when VI is 0, the gate terminal is also going to be connected to ground, right? So VI is the top part of VI is also VG, the gate voltage, right? So if VI is 0, then VG is 0. Well, VG 0 means it is actually down here. Okay, so VG is now down here, and therefore VGS is actually this way, right? So VGS is now pointing down. VGS, because the gate part needs to come down to ground. So then VGS, instead of pointing up like this, it'll be pointing down towards ground. All right. Now, it's worth to redraw the circuit so that we can see a bit more clearly. So here's how it should look like. So if you notice, you have the VGS is positive pointing down, where the plus terminal, if you like, is connected to ground. So this is what happens. So when you do that, your GM-VGS now, right? Because remember, yeah, so GM-VGS is from ground because the drain is connected to ground. So it's from ground to source. So then that's what this is. It's from ground to source. All right. Okay, so now we're trying to work out. Remember, we're trying to work out what output impedance is. So we need to figure out what is this impedance. What is the impedance seen after RS, looking towards the left? Okay. Okay. So what we have here. Okay. So we need to work out what ZS is. All right. So the source impedance, if you like. All right. So we can use Ohm's law for this. So R equals V over I, so ZS is equal to V. Well, V in this case is going to be negative VGS or VO, right? So, the voltage drop here is VO, all right? Or negative VGS, so it's because VGS is pointing the other way around. So it's negative VGS divided by IS, right? Okay, so that's what ZS is going to be. R equals V over I. So the V is going to be negative VGS or VO, positive VO, divided by IS. But then if you look at IS, well, IS is just IO. I mean, IO has nowhere else to go but into the source. So therefore, IS is just IO, right? So let's just write that expression down first. Instead of ZO, let's write an expression for ZS first. All right, so that's the source impedance. So ZS is equal to negative VGS, right? Remember, yeah. So it's just Ohm's law. So negative VGS is because VGS is pointing down, so we put a negative sign there to get the correct orientation, divided by IS, right? So that's what it should be, right? Okay, so negative VGS at the top, and then divided by well, IS is basically IO, right? And so again, VGS can be divided by IO, which we have as negative GM VGS, right? So minus minus becomes positive, VGS and VGS cancels out. All right, so what's left is just 1 over GM. Okay, so the impedance looking into the source is just 1 over GM. So now we can work out what ZO is, the output impedance, because now we have RS in parallel with ZS. All right, so ZO is now simply RS parallel with ZS. Okay, or RS parallel with 1 over GM. Okay. Oops. Okay, hang on. I need to do something here. Will this work? Let's see. Okay, all right. We'll leave it at that, right? So RS parallel with 1 over GM. That's what ZO is. Okay, so let's move on to the next one, which is AV. Okay, what is going on here? Hang on. Okay, so the voltage gain, AV, is defined as VO divided by VI, right? The output voltage divided by the input voltage. So we have expressions for both of those. So VO is just this, divided by VI, which is just this. All right. So a few things cancel out. Well, just VGS cancels out rather. So what's left is just simply GM RS divided by 1 plus GM RS. Okay. All right. So now let's finally look at the last component, which is the current gain. All right. So the current gain is defined as the output current divided by the input current. Okay. So IO is just this. And II is just this. All right. So VGS obviously cancels out. So then the answer is going to be negative GM. RG, yeah. So the RG in the denominator goes back to goes to the top, divided by 1 plus GM RS. Okay. So that's it. Thanks.